Anyway, it's not like that at the master's level. It's fun. If you want to do a 4+1 and you like math, like it's worth thinking about. You do, but normally what happens is people do something for their senior project that leads the way towards what their master's thesis is going to do, right? And normally when people do a senior project, you've already picked a professor or two that you like that either work in the area that you're in or that you get along with and you think you would enjoy working with. And so normally that relationship continues from your senior project to your master's thesis. I mean, you don't have to do a thesis. So, other people don't do a thesis. You just take oral exams instead. And those, man, oral exams, that's like taking a final in every class you took in graduate school, all three, and we're supposed to ask questions for 45 minutes each. So it's like a 3-hour conversation where we dive deep and grill people about what they know in their classes. And that I think is more stressful than doing a thesis defense. So just, pick your flavor. What do you like? What kind of stress do you like? Tyler, Jacob, Alston, Gabby, Leslie, Warren, Will, Green, Matthew, Lucas, Jacob, Lena, Lalia, Thomas, RJ, Steve, Ryan, and so I said it in my announcement, I will say it again. This was a marked improvement over the first exam in the quality of the mathematics that you're writing, even when you guys didn't really, so you had an idea, but you missed what that idea was. The quality of the mathematical writing is like remarkably better. There's one exam I have not graded yet. Because it was taken outside my office, outside of regular times. I will get that done this afternoon. Okay. What was I going to say about that? Yeah. So anyway, good job. This is a much better exam than the first one, and I thought generally overall the class improved a lot. And even if the score ended up looking similar, I would say that even with people that end up with the same scores. Because I'm evaluating a combination of style and content, even if the content was wrong, the style of the theorems was better. The approach to the arguments was better. The structure of the arguments was better. The writing was much clearer. So I'm very appreciative of the amount of work that you guys have put into this. So on this exam, because the average score on this exam was almost 10 points higher than on the last one, I think. I don't think that this exam is going to come together with an exam revision thing where I can give you guys points back. You can come argue with me about that if you want to, but there's not a lot of time left, and I want to put the focus on how we're going to finish the class here. So what you should do is you should think of this exam roughly. You can think about this exam, the scores in this exam as corresponding to percentages, but I would actually consider the range of scores I got here this time to range basically from a C- up to an A. So if you find yourself sort of at the bottom of the range, think of that as a low C, or a high D, low C kind of thing, where you're right on the verge of full-blown passing C or high C or something like that. And I'll tell you, the most common mistake that cost people that should have gotten higher grades than they did was quite a few people only proved 1/2 of an if and only if statement. And I wish they'd be higher than that. because half of an if and only if is I can only give you half the point, right? So if you got questions about how your exam specifically was graded, you can come talk to me about it. Recognize that the same ideas that we talked about in here are going to show up again. The final is not just going to be about chapter 6. I don't know if you guys noticed or not, but basically every question on this thing was a homework question or a question that was on, this was completely accidentally, by the way, a question that happened, this question about U and V and U plus V, I was like, what a great question, I'm going to put it on. I've been talking about it with the media and in the hallway, and then it was on the exam review guide. So the one question on here that was not a homework question, and even if I think was a homework question that wasn't assigned, was on the review guide. So make sure you take the time to do the prep. And it's hard to ask good questions. It's likely you're going to see these homework-like questions again on the phone. Okay. I have little bits and pieces to hand back here. So if you've been missing things from me, I cut my way through a large pile of what's left. If I've been missing things from you after this, there's a few that I haven't downloaded from email yet. Because I did this at home last night and I couldn't print stuff. I will have that back. I mean, those will be done tonight. So like, there's a few that you have, for example, that I haven't downloaded yet. So my backlog is basically clear, I think, except modulo maybe 4 or 5, like assignments that came in really late, I still have to grade. So questions about individual grading, I'm happy to answer after the class. Remember that I build my grading scale to make sure that 1 or 2 point deviations in your test score don't make material changes in your final grades in the class. So like, oh, I have to get a 36 instead of a 35 or a 42 instead of a 41 because I get an A or a B. 1 point on one exam shouldn't make my exam grading or my grading system is set up to be robust against that. Because I admit, like, you know, I have very clear ideas about what's worth what. Make sure you add up the points in the front of your exam. If you happen to find an error in your favor, you're under no moral obligation to report that. If you find an error against you, please let me know. Any broad questions I can answer before I go home? Homework questions for the final too. Homework questions for the final. Like prep, like oh yeah. Okay. Yeah, I'm gonna send you in blind. Isn't this final on Friday? Yeah. You guys got a million years to get ready for this test, right? So yeah, you'll get the same, even if it was on Monday, you're gonna get exactly the same thing you got before the midterms. I mean, it'll be kind of cold to send you in blind. Yep. So like this part, the usual, it's a good question because in a lot of classes, what it ends up saying is like, professor's like, well, I'm going to put half the final on the 1 week of material that we've covered at the end here, right? So it's not going to look like that. It's going to be equally apportioned out basically among the same ideas that we already had before. So it's going to be like, you can imagine on a final, the final is going to look like, the model for a final would be exam 1, an exam 1 like thing, added together with an exam 2 like thing, added together with maybe 1 or 2 questions about this late material on questions on 6. So it should be equally spread out across the whole class. Yep. Yeah. So the idea with the final is it's a 3-hour period, but I try to write it to be about 2 hours. 210. I mean, invariably what happens is people sit here for 3 hours and stress and sweat bullets about what they do on the final, but it's supposed to be about double the length of the midterm. So I can't do like 5 questions from exam 1 and 5 questions from exam 2 and then 2 questions from exam 3 because that would be too many questions. So I'll have to cut down so I make an exam that's like a 2-hour exam. Anything else? Okay, so let's talk about, I think last time we left off, we were talking about inner products and how an inner product is like a dot product. So, oh, also you guys, I don't know if you've noticed or not, but about 1/5 of the department is sick right now. So I'm not sure if what's happening is, there's all likelihood of people that are out for like various COVID tests. So like if you're, keep yourselves from getting, the flu is going around and colds are going around and COVID is going around all simultaneously. Try not to get sick. Like there, what else can I tell you? Okay, so let's talk about inner products. So I'm going to remind you the properties of inner products. And then we're going to talk about derived properties of inner products. And remember, the motivation here the motivation here is that we ultimately, so our goal is to be able to solve the problem AX is equal to B, where B is not in the range. Sorry, we should put this in operator language here. I don't know why I'm writing vectors all of a sudden. We want to be able to solve TV is equal to W, where W is not in the range of T. This is the goal, to be able to come up with some meaningful answer to this question. Find B, or at least the best we can. So we're trying to solve a question with no answer. And to do that, remember that our sort of the goal that we're going to use to solve that goal is we want to build an idea of projection. We want to build an idea of, and that's the whole point of all this inner product stuff, is to build projections of vectors. Come up with a notion of orthogonality, come up with a notion of projection. So an inner product, to remind you, has the properties that the inner product of V with itself is greater than or equal to 0 for all V in a vector space. 1, 2, that VV is equal to 0 implies that V is equal to 0. 3, that plus V inner product of W is equal to UW plus VW. These are all the definitions. It's the definition of the inner product. These are the linearity properties. Lambda UV is equal to lambda U dot V. And then finally that UV is equal to complex conjugate of the dot product of V and U. So conjugate symmetry. So we define anything with these properties to be an inner product.
Can you explain the conjugate symmetry again?
So the reason is because the natural idea of symmetry in complex vectors is that you have to deal with a complex conjugate because of rotation. Yep. I'm going to explain that, yeah. So you can't drop it inside, but you can spread it out around individual objects. The basic idea is that when you start computing dot products of complex numbers, right? What do we want a dot product to be able to do? What should a dot product do? In Euclidean spaces, we have that U dot U is equal to the norm of U squared, right? Yeah. Okay. So the fact that we're going to use this conjugate symmetry, basically the reason this happens is because we want the Pythagorean theorem. It's going to show up when we're going to prove a version of the Pythagorean theorem, and it's going to require that we have conjugate symmetry in order to do this. I can't really tell you. I mean, it has to do with rotation. It should become clear as we go. In fact, Axler himself, I think, walks you through why you should use conjugate symmetry here in not absolute value here. I guess one way of thinking about it is that if you take a number A plus IB, which is a complex number, and you multiply it by A minus IB, what happens? Well, you get A squared plus IAB minus IAB plus I squared, minus I squared B squared, just by distribution. And so you end up with A squared plus B squared. Because negative I squared is -1 minus -1 of B. So if you take a number Z, let's say lambda, and you multiply it by its complex conjugate, you end up with that. But what is that? That's the length of lambda squared. So if you took lambda and you multiply it by its complex conjugate, you get the length of lambda squared. This is sort of what underlies the idea that I want this to happen, right? That somehow complex conjugation is built into the idea of using dot products to define length. If you don't get it, you got like I'll point to you where you can read through it more slowly in Axler's book. Yep. So the second position you can derive from these properties. So that's the very first theorem, is like the second position also turns out to be not linear, but conjugate linear. I should point out here when I say this is an inner product on a complex vector space. If you have a real vector space, you don't need, then it's just u dot v is equal to v dot u. And you guys have seen it in the past. That's the sort of symmetry that you have, right? I'll see if I can cook up a better explanation of what's going on here too. Okay, so that's actually the first theorem. First theorem says all the rest of the properties that you want to have in an inner product also hold. So, for example, you get all this, right? So if V is a vector space and this is an inner product on V, then each fixed u v, the function that takes v to uv linear. V 0 u is equal to 0 for all u and u. That's nice. So the idea when you set up mathematics like this, the idea is to give the minimum number of properties you need to build the definition that then induce all of the rest of the properties you need. You're trying, like, it's sort of it's called what's called parsimony. It's a theorem of the philosophy of science that you should work with the minimum number of stuff that you need to define or to lay out the rest of the properties you need. So also, once you have that, you can show this. Now we're going to get the conjugate linearity. So if I took u and I'm added it to v plus w, this is equal to uv plus uw. So some split in the second slot. But because of this relation, it turns out to be the case that if you want to take a scalar out of the second slot, you get the complex conjugate of the scalar. Now, what I want you to think when you're looking at these properties, what you should have in your head is that we are doing nothing here that is not just regular old, the prototypical example of an object that does this is the dot product on CN. Yep.
Why does V not have to be
because you can define an infinite inner product on an infinite dimensional space. In fact, I'm going to write one down. It's a good question. In fact, the most interesting to me, the most useful finite dimensional inner product is the regular old dot product. But you can define an inner product on families of functions. So, in fact, I think Axford gives the example. Does he use L2? Yeah, so he says, okay, consider this set. So this is continuous functions on the closed interval from -1 to 1. That's a vector space. If I take two continuous functions and I add them, I get a continuous function. If I take a continuous function, I multiply it by a scalar, I get a continuous function. So this is a vector space. It's an infinite dimensional vector space because every polynomial is in here. The space of all polynomials is an infinite dimensional space. So this is infinite dimensional. And you can show that if you took an F and a G that were contained in the continuous functions from -1 to 1, you can define an inner product FG by taking the integral of F times G dx. Now that does not look like the Euclidean dot product. But it kind of does, because what does the Euclidean dot product do? It takes the values of the first vector and multiplies them by the values of the second vector and then adds them all up. This is the same idea. It takes the output from F and multiplies it by each output of G and then adds them all up. But since it's continuous, it has to do with an integral instead. So this is a function version of an inner product. And you can go through and check. This satisfies all these properties. Is it the case that if I switch the order of F and G, I get a different integral? Everything we're doing here is real valued, so you don't need to worry about like the complex conjugate in this case, right? Since everything is real. Integrals are linear. If I put like two functions here and I added them, I could get two integrals by splitting them. I could take a scalar out of an integral without changing it. So because integrals are linear, they end up being inner products if you set them up this way. Yep. Well, an inner product in any one case is a specific thing, but yeah, there's lots of things that are inner products.
So there are like multiple inner products.
There's tons of inner products. In fact, this is not the only inner product from the continuous functions from -1 to 1. Another infinite dimensional inner product is this one. So suppose I give you, I gotta be careful with this one to make sure that it adds up. Suppose I tell you that I have sequences that converge when you add them up. You guys have seen these before in calculus, right? Infinite series that add up. So suppose that you have A1, A2, A3, dot, 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 so that the sum of the AIs converge absolutely. And you have a different sequence, B1, B2, B3, so that the sum of the BIs converge absolutely. Gotta be a little bit careful here. It's not enough to converge absolutely when I start multiplying. So I need it to be this. I need the sum of the squares of those things to add up. So square summable sequences. Then you can just take it, you can make an inner product here by doing the infinite sum. You'd say, oh, well, if these things add up when I square them all, and these things add up when I square them all, then I can take this infinite sequence and I can sort of inner product it with this infinite sequence by just doing the sum of, it's like sort of a gigantic Euclidean inner product, right? You just do it forever. There's another infinite dimensional inner product. So yeah, basically, when you fix a space of objects down, if you're lucky and it's nice to work with, there'll be some or several like obvious choices for what you'd like to be the inner product. And they're all basically built off of the idea of like multiplying elements of the objects together. So, okay, that question is one of the central questions of Math 412 and Math 415 and Math 414 and Math 550. What you just asked is, are metrics induced by inner products equivalent? You might not know that that's the question you asked, but that's the question you asked. And the answer is, with inner products, that answer is yes. But you have to go through a lot of proofs to get to the point where you can even make that question meaningful. But yeah, that's a deep question. When are distances somehow equal to each other or related to each other? And even then, I lied to you because there's other conditions you need to say in order for them to be equivalent. Okay, how about a nice regular old inner product? The best possible inner product, which is if you have Fn, then this is just equal to this. So in Fn, the inner product is just the regular old Euclidean dot product. But this is the standard inner product. On Fn, which is the one that you already know, right? You take a vector u and a vector v contained in Fn, and then the inner product of u and v. If nobody tells you differently and you're working in Fn, you just assume that you're just working with regular like this. K is equal to 1 to n. K. It's a standard dot product. Just written out in the notation that people like to use. So if you hate summation notation, you could take u1 v1 plus u2 v2 out to UN. I know some people hate sigma. Yep. No. Actually, yes, but you should. It does actually, because the coordinates are going to change, right? So I'm representing this with coordinates in the standard basis. So we should be careful here to say that the action on coordinates doesn't change, but the vectors might have different representations in different coordinates based on the basis. So yeah, the basis is a sort of intrinsic in what we're doing. Okay. If it's not an FN, either you just think it's a thing that acts like a dot product, that set of rules, that 10 rules that I wrote down, or I have to tell you specifically what the inner product is in that context. I have to say it's a vector space, and here is the specific inner product that I want you to use. So either it's an abstract thing that like it's just a function that satisfies 10 rules, or it will be a concrete thing that somebody has to tell you what it is. So if I just tell you something's an inner product, all you know about it is it behaves nicely with respect to algebra. So let me show you kind of what I mean by that. So let's actually prove, using the definition of an inner product. So we'll use the definition of an inner product to prove that U lambda V is equal to lambda bar. That's not part of the definition. That was part of the theorem, right? That was like, I think, condition 4 or 5 of the theorem I wrote down. Okay, so let's use the definition to prove that. How will we do it? Well, I don't know anything about what's happening in the second slot. So I'm going to start by saying, let's let U and V be in the vector space, and let's let lambda be in the field. Okay, well then, U lambda V, how can I get this so that the lambda, if it was in the first slot, I could do something with it because the definition says if the scalar is in the first spot, I could pull it out. How can I move it there? Oh, I can take the conjugate of it. So I could write this as lambda V comma U conjugate. That's because symmetry, conjugate symmetry was part of the definition. Now I've got the lambda in the first slot, so I can take it out. Now, the nice thing about complex conjugates, as you said, is they distribute across products. So if I have the complex conjugate of lambda of this number times this number, I can rewrite it as lambda bar times this. So I can split the complex conjugate up. This is one of the rules of complex conjugates, is that if you have ZW bar, it's Z bar, W bar. Complex conjugation spreads out across some. I'm almost done. I can just put this back. So what we've shown is that we use properties of the definition to prove that this thing is conjugate, like sort of, that it's conjugate homogeneous in the second slot. I can pull scalars out of the second slot, but I have to complex conjugate them to do it. And this is typical of the way inner product arguments look. Inner product arguments, this is the 2's question about what do you do if you don't know what the inner product is. All we have is the algebra. We don't actually know what the inner product is, but we know it follows all the algebraic rules to do this. So these kind of arguments go like this. So as an exercise, you should actually see, I'm going to give you an exercise here, which is do not look at the book and prove that theorem. So you can go to the book and you can read that theorem that gets you the other 5 properties of an inner product and try to prove them directly. Prove that theorem without looking at actual proof. Use the definition, so just in the way we use the definition to show that this property held based on properties only from the definition. See if you can show the rest of the properties. So that theorem has lots of properties about what happens in the second slot. Okay, so the very next thing that we're going to do with inner products is we're going to say, well, in Rn, we had this relationship that said that if I took x and I dotted it with itself, I got the length of x squared because of the distance formula, right? This is just one of the features of Rn. If I take a vector and I dot it with itself, that's like saying x dot x is x1 squared plus x2 squared up to plus xn squared. But that's equal to the same thing as the length of x those are the same, right? The dot product of a vector with itself is equal to the length of a vector squared. So with inner products, we don't have a notion of distance built into an abstract vector space. So we're just going to define a notion of length. This came to us from the distance formula. The distance formula is pretty great, but if I don't have a distance formula, what can I do? Well, I can make one. So I'm going to make a new definition called norm. The norm of a vector. And really Axler's lazy here because he means the norm of a vector induced by an inner product. And you might ask, why am I going out of my way to specify that this is induced by an inner product? And the answer is because there are norms that don't come from inner products. And you'll see those in analysis. So the norm of a vector is defined. This is a definition. We define the length of a vector to be equal to the square root of the inner product of the vector with itself. So we make that the definition of the length of a vector. And the reason we do that is because that gets us exactly what we wanted in regular old Fn. In Fn, this is the same definition. Now I know the temptation when you write an expression like this down to say, can't I just write that down as v1 squared plus v2 squared plus v3 squared and all the way? And the answer is no, you're not allowed to do that. As soon as you do that, you're working in coordinates. We don't want to do that. We want to think about, we don't know what the inner product is. So we think about it abstractly. I give you an inner product. You don't know what it is, but if I give you an inner product, you can already immediately define a notion of length out of that. So inner products are really cool because they're going to build both length and angle, it turns out. And norms turn out to have properties that act just like distance. Suppose V is in V. Then the length of V is equal to 0 if and only if V is 0. Yeah, that's nice. I mean, if I'm going to have a notion of length, it better be the case that the only thing that has 0 length is the 0 vector. How do I prove it? So again, I find these are the sort of arguments that are they're less abstract than working with vector spaces because you're just doing algebra. You got to be a little bit clever. So assume that the length of V is 0. What is the length of V? How do we define it? Well, it's this, right? Oh, that means that the square root of the inner product of V with itself is equal to 0. I can square both sides of that to get the inner product of V with itself is 0. And what do I know about the definition of an inner product? What is the only vector that has its, if I take the inner, if I know that I've got an inner product of vector with itself is 0, what's V? It's got to be 0. So V is 0 by definition of inner product. So if the length of a vector is 0, then the vector is the 0 vector. The other direction is even easier. Suppose V is equal to 0. Then what's V inner product with itself? 0. The inner product of V with itself is 0. If Z is the 0 vector, the inner product of 0 with 0 is definitely 0. So that's 0. Oh, but that means the square root of the inner product of V with V is equal to the square root of 0, which is still 0. And that means that the length of V is equal to 0. What's up, Lauren? This is the definition. This is an example of the motivation for the definition. In the context that we're working in, when we say norm, we automatically mean this is true. And I will tell you that generally, because people hate square roots, another way to make this definition that's equivalent is to say that V comma V is equal to norm of V squared. And then there's no square roots at all. But yeah, it's with reference to this function that you may or may not know. You know there's a function called the inner product. You might not know what it is, but you know that it induces a way of measuring length. Yep.
When you square and when you check the square root, does that work for all space?
It does, because remember what the inner product does is it eats vectors and spits a number out. This is a number. Inner products make numbers come out, and numbers have square roots. And not only is it square root, this number is a positive number. Remember, the reason I'm allowed to do this is because when we set the inner product up, we said this has to be true. The inner product of a vector with itself has to be a positive number. And that means this is a well-defined operation. I'm always allowed to just take a square root of a positive number. That's okay, or non-negative number. Okay, so inner products are great. Look, we're taking an abstract vector space, which doesn't have any notion of geometry at all, and we're putting it back in. We already have a notion of length, but vectors and the way that we think about them in Rn have two properties. Way back at the beginning of the class, I asked you guys what a vector was. Way back. And a bunch of people said something with magnitude and direction. That's what you learn when you're doing, Euclidean vectors, right? A vector is a quantity that codes magnitude and direction. Well, there's magnitude. If we have an inner product, we have a notion of magnitude. Where am I going to get an idea of direction from? Well, let's remember, we could use Rn to motivate a definition of distance, right? We use the way that it works in Rn to say, let's make that the definition of length. I'm doing the same thing. Why don't we say, what if I have a vector and another vector, and I take their dot product and I get 0 out in Rn, What does that mean about X and Y as vectors? No, that's true. If they're 0, that'll be true. But if it's possible to have this happen when they're not 0. So like, for example, if you have this, that dot product turns out to be 0 plus 0, which is 0. So it's possible for that to be 0 when it's not the 0 vector. What does it mean about the vectors? They're perpendicular to each other. Now, am I going to give you a hard time about the difference between the words perpendicular and orthogonal? No, the same word. One comes from Greek, one comes from Latin. Who cares, right? Like, I'm not going to take points away from you because you used the wrong one, right? The idea here is that when x dot y is equal to 0 and x and y aren't the 0 vector, and additionally x and y aren't 0, that holds whenever this is true. So with distance, we had a notion where the dot product of two vectors was equal to the distance formula, and we use that to make a definition, but there is no notion of what it means to be, there's no angle in abstract vector space. I don't put a V and a U down in front of you and somehow you're going to say, oh, measure the angle between them. You can do that in Rn, not in an abstract vector space. What can you do instead? We can make the definition of perpendicular, or the definition of what our orthogonal be. If the inner product is equal to 0, then we define those to be vectors that are orthogonal to each other. In the same way that we use this to motivate our notion of distance or length, we're going to use this Rn idea to define a notion of, it's loosely a notion of angle. Not I can't tell you if things are 23 degrees away from each other, but I can tell you if they're perpendicular or not. Yep. We don't care about any other number. We don't. No, the basic structure here is we don't care about any other number. It's hard to interpret what it means, like in an abstract vector space, any number other than they don't point in the same direction. There are ways to do it, but they're way beyond the scope of what I want to talk about. So we're going to make this following definition. We say, let U and V be in V non-zero. Then U is perpendicular. Sorry, I said perpendicular. I'll use orthogonal instead. U is orthogonal to V if U inner product V is 0. So we make it not just a property, but the definition of what it means to be orthogonal. So inner product spaces are amazing because you don't just have abstract vectors flopping around that you have no idea how they interact with each other. As soon as you have an inner product, you have length and a notion of angle that we can use to build projection. Okay. So inner product spaces have all kinds of, it's like a vector space and more, because you get all this extra structure that comes along with it. Hey, should we want you, sign up for a year subscription? Get yourself an inner product space. So an inner product space is a vector space plus an inner product plus a norm plus orthogonality. So this is a way of kind of getting the linear out, the vectors and the vector analysis back into abstract linear algebra. So this is the first time where we get to see, maybe we can now do stuff that we did in 206, right? In 206, we talked about vector projections. Well, this maybe gives me an idea that I could define projections, because projections require a notion of length and a notion of orthogonality, right? Every time we did a projection, the idea of projection, I'm going to remind you of the last property I want to talk about here before we go further, which is, I'm going to remind you in, say, like in R2. Here's about the baby case, R2. I've got some vector B, and I have some vector A, and I want to take B, and I want to project it down here onto A. What is the relationship between this vector and that one? Well, they're orthogonal to each other. I guess you could say perpendicular, right? They're orthogonal. This is an orthogonal vector to this vector. There's a 90-degree angle right here. This vector is called the projection of B onto A. And remember, this was defined to be equal to A dot B over A dot A times the vector A. And then we had this vector up here. And if you dig in your mind deeply enough, you'll remember that Stewart, for whatever reason, calls this orth. Probably for orthogonal complement. I don't know. Stewart's weird. He calls it orth. I didn't choose the notation. Let's just call it, I'll give it a different name. I'll call it W. What is the formula for W? How do I find it? And I can find it. Yeah, I promise I can find it. So take B and subtract this projection. And that will be the definition of this vector. So this vector and this vector are called, this is called an orthogonal decomposition of V. The claim here is that this vector is perpendicular to this one. These vectors are perpendicular to each other. I mean, I drew a triangle, therefore I proved it. Right? This vector and this vector are orthogonal to each other. That's this vector and that one. At least if you believe my sketch, you should believe that's true. And also, the projection of B onto A plus W is equal to the original vector B. So once I've got a notion of distance and a notion of orthogonality and a notion of dot product, I can take a vector B and I can yank it apart into orthogonal pieces. The piece that comes from the projection and the piece that's left over. Two vectors that are perpendicular to each other that add up to the original vector. Those of you that have spent time doing free body diagrams have done this till you're blue in the face. This is the picture that I want to rebuild in the abstract setting. So how am I going to do it, do you think? We've got all this crap now. All this stuff where we have like inner products and a notion of length and a notion of orthogonality. What do you think the solution is to defining? Suppose that you just like had some pie in the sky idea, like, man, I would really like to take this idea and make it work not in Rn or in R2, but in abstract vector spaces. Any ideas? Those of you who've not read ahead in the book.
Inner product, dot product.
Well, that would be a really easy idea, wouldn't it? What if we could just take the dots out and put inner products in instead? That would mean another way that we could use our ideas from the way it works in Rn and lift it up to abstract vector space. This actually turns out to be exactly what you want to do. The way that we're going to talk about it next time, so I don't have time to go deeply into this time, but we're ready to define the idea of projection. Once we have an idea of length and orthogonality, we can do all kinds of stuff. We can prove the Pythagorean theorem. We can prove the triangle inequality. We can prove vectors have orthogonal decompositions in terms of projections. And the naive idea turns out to work, which is we can define the projection of a vector u, v onto a vector u. We define it this way. And that definition of projection is going to turn out to be good enough to recapture everything about, remember, ultimately the goal is to solve these impossible problems. That's what we're going to be able to do with this. All right, that's enough. Thanks for your patience.